So next we have Samuel Liu, who will be telling us about cosmic ray transport using the CGM.
All right, everybody hear me all right? I'm Samuel Liu. I'm currently a licensed surgeon PhD student at UC San Diego, and thanks to Neil for introducing me about what I did in filaments this morning. So I'm not going to talk about filaments anymore. I'm going to talk about something slightly different, which are cosmic tensor models and how to use the CGM property in observable constrainment. So this is part of the huge fire simulation project. There's been many very good fire talks the past few days, so I won't spend time introducing fire again. What I do want to spend a little time to introduce here is cosmic rays, considering I'll be the first person, probably only person talking about cosmic rays in this workshop. So what are cosmic rays? They are very energetic particles. They're mostly protons, and they're mostly generated from supernova shock and aging jets. About 10% of the supernova energy gets transferred into cosmic ray energy, and this number has to go down to about 2% of the AGS. In the low pole interstellar median, what I mean here is the solar neighborhood. The cosmic pressure is roughly in approximation with all the other pressure components like thermal pressure, magnetic pressure, and turbulent pressure. But this is not true for the CGM or other galaxies. So one of the most important observational facts about cosmic rays is although the full energy spectrum of it spans over a wide range of energy all the way from a few million electron volts to the GZK limit, about more than 80% of the species have energy density just concentrated over this very narrow band of energy, which is about 1 to 10 billion electron volts. This is very important. It's actually motivated us to model the cosmic ray just to live in single energy spectrum in our fire simulation. And that's actually most fire simulations are doing right now. So those are the observational overview. But what about the physics? So the key physics for cosmic rays propagation in the ambient surface gravity median is a combination of streaming and diffusion. So the classic picture for ray transport is so-called p-channel scattering processes. As you can see from this animation, about how cosmic particles are scattered along magnetic field lines. But this happens on a gyro radius field, which is about only a tenth of the AU in the typical interstellar medium density environment. So this is super small. You have to go to the microscopic physics of cosmic rays in order to actually resolve them in simulations. So people have, worked this out 2 years ago, and if you just look at this transport equation, all the terms like the streaming laws, collisional laws, source term, they can be determined either from intrinsic properties of galaxies or just be constrained from observation pretty well. There's only one thing here, although, cannot be constrained pretty well, which is this diffusion parameter. It has two components, which is the parallel diffusivity and the streaming velocity. So only two things are unconstrained, but if you go back to the microscopic description of cosmic rays, both of them can only be determined by this scattering rate, nu. So only just one parameter that is unconstrained. The whole problem of cosmic ray propagation just boils down to how to model diffusion. There are many models available. Phil Hopkins has this list of 30 more models, but among them, there are only 3 of them that are most prominent and pass the very fundamental basic gamma ray constraints. So those models are the constant diffusivity model, which has a spatially and temporally constant diffusivity about 3 times 10 to the 29 centimeters squared per second. This value is just constrained from the basic gamma ray observations. We also have 2 other physically motivated models that have a variant diffusivity over space and time. For the first model, it changes in turbulence. We assume the cosmic rays are scattered from the ambient pre-existing turbulence. And for the second model, self-confinement, we assume they are scattered by themselves, the self-excited alpha wave. And the important relation here is that the diffusivity kappa is inversely proportional to the cosmic energy density. This is what we mean by confining by themselves. Worth commenting here that all those simple models that pass the basic gamma ray constraint, as mentioned in TK Chan et al. 2019 and Phil Hopkins et al. 2021. And we do have 2 spectrum cosmic ray runs. All those models here, however, they're running single beam cosmic spectrum, as I mentioned in the first slide, because most of the energy is concentrated around this very narrow range of bands, so it's a very good approximation to have them to being a single beam cosmic rays. Those reruns, they're restart from redshift around 0.05. All those runs, so they are run from the very beginning. All right, so much for cosmic rays. This is a CGM thing. So how do all these affect CGM? In fact, they do, and they do that in many significant ways. For example, they can alter the phase structure of CGM. They make the CGM gas to cool down much more efficiently. They can also change the dynamics of the CGM. For example, they can change the inflow and outflow pattern of galaxies. They can interrupt the galactic fountain to create more outflows. And last but not least, as recently discovered by Sam Kanada, the synchrotron emission feature can be very dependent on a cosmic model. Those are just a few curious words about how cosmic rays can affect the certain galactic median. We actually want to reverse the logic and use those properties and observables to constrain the cosmic model further. So we selected M12I galaxies from fire simulations, which are Milky Way mass galaxies. We classify them based on the physics implemented. We have cosmic ray, non-cosmic ray runs. We have single beam cosmic runs, full spectrum cosmic runs. We also have different specificity models for cosmic runs. The first thing we looked at was the gas morphology. Although being very qualitative and hand wavy, it could still be a pretty good indicator of the validity of the models. So comparing to the constant diffusivity cosmic run on the left, which has a clear gaseous disk at redshift 0, as all the other M12I galaxies do, the extrinsic turbulence models, although they're like more turbulent and a little bit different, they still have sort of a disk, more or less. But this feature is completely missing in the self-confinement run. And we suspected this is because an explosion happened a little bit earlier between redshift 0 and redshift 0.2. The reason for those explosions to happen is because the diffusivity is scaled inversely with respect to cosmic energy density. More cosmic particles being gathered at a center of galaxy means a slower diffusion, which makes more particles to gather at the center of galaxy. So this piling up of cosmic particles induce a non-thermal pressure support from the center of galaxy that expels out of the gas eventually. So a disk was formed a little bit earlier, but the cosmic ray effect seems to be pretty detrimental to its formation in those ways. So in the next few slides, I'm going to show several comparisons between our simulated galaxies and the observational data. The first thing we wanted to compare to was the ion absorption column densities, and those were data from Halo survey as appeared in Polchaska et al. 2017 and Jessica Work et al. 2014. The stars are the observational data, and the lines are our simulated galaxy. So looking from the left panels to the middle panels, we saw that the cosmic rays boost up both the hydrogen-1 and oxygen-safe column densities by a few orders of magnitude, making them closer to the observational data. This feature is not the same; is missing again in the variant diffusivity model. So the other lines in the middle panels are lower than the blue line. That means the ion densities are rat back again. Going from the middle panels to the right panels, we saw the two spectral runs are very alike the constant diffusivity cosmic runs, regardless of the galaxies they're residing. And this is because they're restarts from constant diffusivity runs from redshift 0.05, and we could have just simply herded everything from the random runs. And then we went to the X-ray emission comparison. We first compared to the data from the Rosate survey as appearing in Michael Anderson in about 2016. They had both the total emission from the galaxies as well as emission from the CGM. The CGM regions were defined in that way. We saw that the total emission, our total emission agrees fine with the observational data, whereas the CGM emission was completely off by a few orders of magnitude. We went to another survey, which is a much newer and more novel survey, Eurostata survey, appearing EGN et al. 2024. It's very new, at least when I was preparing for this slide. I don't think this has been accepted yet. But we saw the similar trend, namely the total emission agrees fine, the CGM mission was wrong. And we suspect that the reason for those failures of the comparison was that those survey data, there's used stat galaxies is just the property of one single property, and then our zoomed-in simulated galaxies were very individualized. So there could have been a bias between survey data and the individual zoomed-in simulated galaxies. So we went to another comparison. Those are individual star-forming galaxies paired in Li and Wen in 2013 in the Chandra Observatory. So those are individual galaxies with more rigorous sample selection and source removal procedures. And we saw that since they're individual star-forming galaxies, our simulated zoomed-in galaxies, they agree with them better than the survey galaxies. So just reflat and give a little overlook of comparison we've done so far. We admit that proxy models are still very unconstrained, and observational data, especially those large survey data, stats from large survey may not be suitable for comparing with our zoomed-in galaxies, and we might be able to distinguish between different cosmic transfer models better when we have more compatible samples of individual galaxies to compare with. And other observational signatures such as gamma ray emission feature, Faraday rotation measure, synchrotron radiation features to be used to compare in the future. People have done those comparisons between constant diffusivity cosmic models, but they haven't done anything for the variant diffusivity model to put a better constraint on the model. And they're open to comparing with any other observational data. And if the observer here has anything off the top of the head, I'll be happy to discuss. And I'll just leave my summary here and I'll take questions.
Thank you, Samuel, for that great talk and for keeping on time. We'll take a few questions.
So first, just to clarify, because it went by quickly and I missed it, for the constant diffusivity, when you're doing the full spectrum runs, are you assuming the diffusivity is independent of energy? So I would think that would already violate one important constraint, which is the gamma ray spectral index of the Milky Way and other star-forming galaxies, which is that, right, I mean, when people make, say, Galprop models of the cosmic ray population, the reason they assume an energy-dependent diffusion is because otherwise you wind up with the gamma ray spectrum having the same slope as the cosmic ray injection spectrum, which is minus 2.2, which is way too shallow. So are you using that as one of your constraints?
I am not very sure off the top of my head at this moment. I have to go paper later, but it says it's constant diffusivity. It's not exactly like precisely constant. It changes slightly as the cosmic evolves, so that might be something that compensates it.
Okay, but it's not changing in space and time that's important. It's changing with respect to cosmic ray energy. That's the main constraint that you have from the gamma ray spectra, that it has to be dependent on the cosmic ray energy.
And one more over there.
Hi, Sam. Thanks. This is super interesting. I wonder, the very strong effects that you showed on the CGM phase structure, those results were for a specific version of your cosmic ray diffusivity model, or is that kind of very generic and that happens with almost all of the models?
The plot you saw was a very distinct difference between the MHD and cosmic was in cosmic diffusivity.
But do you see something similar with the more sophisticated models?
Yeah, we did see differences between MHD runs and diffusivity models, but yeah, those are very different. Like each model has a different structure, so it's just different in that way.
Okay, thanks.
Sure.
All right, let's thank Samuel again.